wrote on the board last time. These are the equations that give you these curves for H versus C. You remember we have three different forms of these equations, and all three will be useful for different purposes. So let me write them down. HRS is equal to H0 plus 1 by 4 into R alpha plus S alpha minus the whole thing square, where H0 is equal to 1 by 24 into C minus 1 alpha plus minus is equal to This was form number 1. Okay, this is just directly H as a function of C. And then we had two other forms. The first one was when we parameterized C is equal to 13 into plus 6 into T plus 1 by T minus 6 into T plus 1 by T. Then HRS was equal to 1 by 1 by 4 into R minus 1 the whole thing R square minus 1 T plus 1 by 4 S square minus 1 1 by T minus half of Rs minus 1. Right? This was the parameterization of T, and this was T. There was a quadratic equation determining T in terms of C. Clearly, the two roots of the quadratic equation were basically interchanged by whatever you got for T was whatever you got for 1 by T. Okay, and you can see that this expression is invariant under T goes to 1 by T if you also interchange R and S. And there was the third expression, which will be the most useful for today's discussion, which was C is equal to 1 minus 6 divided by M into M plus 1. HRS is equal to HRS of M is equal to M plus R, M plus 1 into R plus minus M into S, the whole thing squared minus 1, the whole thing divided by 4 into M plus 1. Once again, the two roots, there was a quadratic equation, M and M plus 1 were interchanged in the two roots. Once again, you had M and M plus 1 interchanged. You might think there's a minus here, but it doesn't make a difference because it's squared. Okay, so interchanging M and M plus 1, the two roots, interchanging R and S gives you the same answer. Okay, now the first thing we want to show is that we want to use these expressions to try to argue that that C, when C is greater than 1, okay, there are no constraints. When C is greater than 1, there are no constraints on the theory from unitarity. Okay, there are no constraints on, at least on this matrix of inner products from unitarity. That this matrix of inner products is always positive definite. Okay, so let's consider two. So since C is greater than 1, you see 25 plays a special role here, because you get the square roots of 25 minus C. These square roots go imaginary when C is below 25. Okay, so let's take two cases. First case, C greater than 25. And then let's later on consider C between 1 and 25. Okay, greater or greater than equal to 25. Okay, in the case that C is greater than equal to 25, what I want to argue is that these HRS curves, that this curve is always negative whenever C is greater than or equal to 25. Okay? So let's try to make that argument. Is that would demonstrate what we want, because we want to show that no positive H is constrained when C is greater than 25. Okay? So now let's try to make that argument. Okay. The first thing we do is from here. Let me see. Okay. From 7th. The first thing I do is I solve for m in terms of C here. Actually, I'd written that solution also last time in the class. We have m is equal to minus half, just solving the quadratic equation, plus minus half into square root of 25 minus C divided by 1 minus C. Now let's see. Suppose C is greater than 25. Okay, then this quantity here, then this, I want to argue, then this implies that m lies in the range minus 1, lies between minus 1 and 0. Okay, C is greater than 25. Okay, so let's see. Suppose C is greater than 25, then both these are negative quantities. So we can write this as square root of C minus 25 divided by C minus 1. Okay. Clearly, this quantity starts off when C is equal to 25 at 0. And when C goes to infinity, goes to 1. Okay. So this quantity is bounded between 0 and 1. Therefore, this quantity is bounded between 0 and half. Okay? So then depending on which sign we take, this quantity is bounded between 0 and minus 1. Is this clear? Okay? So this m here, when C ranges from 25 to infinity, m varies in the range 0 to minus 1. Of course, one of the, if we choose one sign, let's say we chose the plus sign, then we would have m varying in the range 0 to minus half. Okay? But then m plus 1 with some minus sign would vary in the other range. Anyway, the other guy varies in the range minus half to minus 1. Okay, great. So this guy is always in this range, whichever sign we choose, this guy is always in this range. Now, when we have this in this range, we have m into m plus 1, this is always less than 0. Right, because m is somewhere between 0 and 1. So either, this quantity is 0 and minus 1. So this quantity is negative, but this quantity is positive. Right? Because we've got 1 plus some number less than minus 1. Okay, so this quantity is always less than 0. That's the quantity that appears on the in the denominator here. Okay? So this quantity will be negative if we can show that the numerator is always positive. Okay? But now let's look at the numerator. The numerator has, remember that m is negative, so we'll write everything in terms of mod m. So we'll write m plus 1 into r minus ms. We'll write that as mod m into s minus mod m into r plus 1, the whole thing squared. Okay, so this is mod m into s minus r plus 1, the whole thing squared. This thing minus 1 divided by 4 into m plus 1. Sorry? Plus r, thank you. Plus r. Plus r. Right. Absolutely. Absolutely. Okay. Now, let's look at the range of variation of these R and S's. You remember R and S's varied from 1 up to, you know, the level, the RS product had to be less than equal, had to be less than L. So we had RS were equal to 1 blah blah blah, but RS was less than L. So RS were integers starting with 1. Okay. Now, this quantity, therefore, I want to now argue that this quantity will always be greater than 1. Okay, so what is the argument for that? Let's see. Let's see. Oh. Let's see. Sorry, give me one. Give me 1 minute. Yeah, let's try this. See, our quantity is R plus mod m into S minus R. R plus mod m into S minus R, the whole thing squared, this quantity. Okay, but now I'm going to write this as in the following way. I'm going to write R as R plus 1, R minus 1 plus 1, sorry, 1 plus R minus 1 plus mod m into S minus R. Now, this okay, so I'm sorry, just one second. Okay, it's true, but give me 1 minute. I had made an argument at some point, but I can't remember. Just 1 second. Give me 1. This quantity is always greater than 1. Why? Should be obvious. Let's see. Let's see. The point is that this guy could go negative, right? The point is this guy could go negative. How negative can it go?
Yeah, so if we take just the base cases, like let's say S or R is either 2 or 1, because we want, like, R is always positive, right?
R is always positive, S is always positive.
And mod m lies between 0 and 1.
Mod m lies between 0 and 1,
so
correct.
you just want that mod m times S minus R is just greater than 0, right?
The worst case would be when this is negative
Yes.
and starts cancelling this.
Yes.
Okay, we want to see that that can never happen very much.
Yes.
Okay, yeah, go on.
So if R is, let's say, 1 and S is, let's say, 2, then that will be positive, right? That the whole expression, and greater than 1 also.
I think you just have to use the fact that R and S are integers, And here, if this becomes negative, R is big enough. I mean, R is greater than 1.
Yeah, but the danger is that S is larger than R, and that this M might bring it very near to minus R.
But S should be less than R, right? For that to be negative.
The S is less than R. Oh, thank you. That does it. Yes, thank you. Okay, let me try to word the yeah. Okay, but even if S is less than R.
Yeah. So now, for it to be negative, R has to be greater than
Yeah. Thank you, Vineet. Yeah. Okay, so Vineet's given us a great argument. So let me paraphrase it. So this quantity R. Suppose, as Vineet says, this quantity is always less than 1. Okay, so the negative part is always this thing which is negative is always less in modulus, the negative part. If it's negative. If it's positive, we proved it, right? Right, so then this is some positive number plus some positive number greater than 1, greater than or equal to 1 plus some positive number, all things squared. If it's positive, it's clear. Let's suppose that this is negative. Okay, now we want to see how large this negative part can be. So the negative part is less than equal to R minus 1. Okay, suppose R was equal to S. Okay.
We can just say that the maximum the negative part can be mod m times R, right?
The maximum the negative part can be is mod m times R.
And
Good.
mod m is less than 1. Right?
But that's not good enough, because then we could get mod m minus 1. We want to show that this is not just positive, but it's greater than R, greater than 1.
Then we can say that R starts from 1, right?
R starts from 1, but we still want to show that this cancellation is not very much. Yeah.
Negative can happen
What?
when S is equals 1, R is equals L, right?
R is equal to L. Okay, let me try to make the argument. Okay, see, let's look at how large the negative part can be. That is the question. Okay, so one case is R is equal to S, then it's just 0. Okay, in that case we've got at least 1 squared minus 1, which is greater than equal to 0. Okay, then we're good. So let's take the case that R is strictly greater than S. Okay, if R is strictly greater than S, then we have R, the negative part could be like the max. Give me 1 minute. The maximum negative part could be R minus 1 into M. The modulus of this negative part can be at most this. Okay, this is less than R minus 1. Therefore, R minus this is greater than 1. And therefore we are done. Is this clear? Sorry for the fumbling around. Okay, so let me just repeat the argument just because I fumbled so much. The argument goes in many steps. First, if S is greater than R, it's obviously obeyed. S is equal to R, it's also obviously obeyed, possibly with inequality. Okay, if S is less than R, then we can get a negative, but that negative part is bounded in modulus by mod m into R minus 1. Okay, but we're adding R to it. So the difference between the positive part and the negative part is greater than equal to 1. Okay, so that's thing squared is greater than 1. Okay, so you subtract 1, you get something positive. Okay, and therefore we have proved that this curve in the region C greater than 25 lies entirely below the h-axis. Okay, so if we look at all these curves for C 25 and greater, the curves lie somewhere here. Okay, and so there is no constraint on positive h's from C lying between C lying above 25. Is this clear? Okay, go on.
So that region does contain the Kac determinant which is strictly positive.
Strictly positive.
These curves always do like that.
Exactly, because we've already seen that at very large h, the Kac determinant is positive, because it's h minus something into h minus something into h minus something. Make h large enough, it's just a product of positive factors. So our Kac determinant is positive at very large h. Unless it cuts some curve, it will stay positive. But the curve never does not exist in this quadrant. So the Kac determinant is just completely positive. Okay, fine. Now what about the region? What happens to these curves when C is between 1 and 25? Actually, this case is even easier because these curves just become complex. Okay? So when C is between 1 and 25, this curve is not a real number, as you can see from any of these expressions. Okay? So this curve just is not there on the real sheet. There is no curve.
M is complex.
M is complex, exactly. M is complex, these HRSs are complex.
If R equals this, that can be a special.
Well,
If R equals this, that can be a
if R equals S, that can be a special case. Let us see. Because you say in that case we have R is equal to S. In that case we have 1 square minus 1. We just get 0. Right? R equals S, we get M.
You will get R.
Oh, R square minus 1. We get, okay, good. Then we will get R squared, R minus RM, no, sorry, R square minus 1 over 4M into M plus 1. Okay. This is correct. If R is equal to S, R equals S, R equals S.
right, then it becomes negative.
Sorry, M is still complex, right? Denominator.
No, but M into M plus 1.
M into M plus 1 is this. So good. Let's work it out. Actually, let me just see what the book says about
So,
it.
1 over M into M plus 1 becomes 1 minus C over 6.
Right.
That is a negative number. So, H is.
Excellent. Excellent. That's a great argument. So Karthik's argument was we have 6 over M into M plus 1 is equal to 1 minus C. Therefore, in this case, this quantity must be negative. Okay, we get a positive number divided by a negative number. So that was in that case as well. Right. So you're right, R equals S, it's real, but it still lies below the real axis. Okay. So basically for C greater than equal to 1, for C greater than 1 at least, for C greater than 1, these curves just do not appear in the positive H quadrant. Okay? Because we've got this Kac determinant positive at very large H, it stays positive all the way through. Now, Kac determinant positive does not mean no zero eigenvalues. All eigenvalues positive. It means total number of eigenvalues.
Negative eigenvalues can be there.
Total number of negative eigenvalues is even. Okay? However, this argument that I tried to half spell out for you last time can be used to show that at very large H, all eigenvalues are positive. I will just spell this, say the argument in words to you again, and then depending on how much you would like, we can try to go into details. The argument went this way. You see, the point is that when we compute norms of states, okay, if you have an Ln and an L minus n, we get an L0 in that commutator. Now we're at very large values of H. Okay? So at very large values of H, this matrix of inner products will be dominated by the terms which have maximum number of factors of L0. Okay? So in this matrix, we will have all kinds of factors. We'll have like polynomials in this L0 in the end, but it's the highest power of L0 that will dominate because we are at very large, we're at very large values. Okay, so with this in mind, at any given level, you can make a basis of states labeled by a notion of length of the state. Okay, and the length is defined as follows. Okay, suppose we've got L minus 1, L minus 2, L minus 3. This is something I'm going to call a state of length 3 because I've got 3 L's in it. Okay? On the other hand, at the same level, I could have an L minus 2, L minus 4. Okay? I will call this state a state of length length 2. Okay. Now, you see, this length is not a very well defined notion because if you take L minus 2, L minus 4 and commute through, we can write that as an L minus 4 into L minus 2 plus an L minus 6 with some number because of the commutation relation that gives you Lm commutator Ln. Okay? But you see, these processes always reduce length. So the maximum length term in a state is a well-defined number, is a well-defined notion. Okay. So what we try to do is this. We try to we write states with some choice of ordering so that the length becomes a precise notion. It's a bit arbitrary, but we choose something. Okay? Why is length important? Length is important because if you've got a state of length n, then there will be a term in the inner product matrix where this guy clicks with its conjugate. And you will get an L0 to the power length because you'll get an L minus 2 hitting against the L2, and L minus 3 hitting against the L3, L minus 1 hitting against the L1. You'll get other terms as well, but they'll all be subdominant in powers of L0. Okay? And because these dominant powers are both diagonal as well as manifestly positive. Okay? By tracing through this idea, you can show that in this you make a basis where in the large L0 limit, the matrix of inner products is just manifestly diagonal and manifestly positive. Okay? So actually doing this requires a bit of work, but perhaps you can see the basic idea. Okay? So going through this process at large enough L0, you can rather easily convince yourself that it doesn't matter what other details are there. Okay? This matrix of inner products is going to be always positive definite. Okay? So that statement combined with our analysis of the determinant, which tells us we're never passing through some curve when C is greater than 1, tells us that the matrix of inner products for C greater than 1 is just simply positive definite. Okay. Any questions, comments, or discussion about this point? Okay? This is already something quite important. It's telling us that this unitarity is not giving us constraints for C greater than 1 theories, and as importantly, it's telling, perhaps even more importantly, it's telling us that we will never have Virasoro null states. You might have other null states, but we never have Virasoro null states for any theory when C is greater than 1. This is key because you see, every exactly solved conformal field theory is exactly solved by using the same idea. You look at a null state. Null state is a statement that some combinations of L's, let's say, and highlights the state. We will see an example as we go on. Okay? But that you remember in the last class, we had an operation of how to act some, let's say some L minus 2, for instance, on a field. How that could be written in terms as a differential operator on all the other fields. some differential operation. You remember that? Okay? And so the fact that this null state annihilates the field gives us a differential equation on correlation functions. It gives us a differential equation on all correlation functions that involves that null state. And that differential equation is very powerful and helps us constrain things in a manner we will start seeing today. Okay? So all exactly solvable theories are in the end solved by this idea. Okay? So it's telling us, already this point is telling us that there will be no exactly solvable theories in C greater than 1 unless there is a symmetry algebra that is larger than the Virasoro algebra. We might have null states from some other symmetry algebra, but not just from the stress tensor and its descendants. Is this point clear for C greater than 1?
Should that bigger algebra contain Virasoro algebra?
Yes. In every case of interest, that's the case. So for instance, one case of interest is when you have a superconformal algebra. So the Virasoro algebra is a subalgebra of the superconformal algebra. Okay? But there is more. And then we get these supersymmetric minimal models that can have, C greater than 1. Or another case is Wessel-Minowitten theorem, where you get current algebra. And you get the Virasoro algebra built out of current algebra through the, what is it called? Sugawara construction. Okay? There again we have null states in a more interesting way, even when C is greater than 1. Okay? But purely Virasoro null states will not exist for any theory for C greater than 1. Okay? So these, unless the theory has a higher symmetry, it's not going to be solvable for C greater than 1. This already, at least by the methods we are familiar with today. Okay, great.
Last time when we were discussing C less than 1, you drew that curve like this at level 2.
Yes.
And you said that the values of x within that value cannot give us linearly representation.
Yes.
But at higher levels, I think we can have more such curves, right?
Yes.
Covering almost the entire.
Almost the entire thing.
Those curves will all be like will give us non-unitary representation.
Yeah.
Almost all of them will be covered.
Exactly. So that's what I wanted to say next. So let's say what Pinak said. Just repeat that with a couple of diagrams. Okay. Now let's turn to C less than 1. Once again, the argument that the matrix of inner products is positive at very large values of H is true. That made no reference to C. Okay? So at any level, if you can reach a point, if there is a point that, so let me draw a few examples. Let's say that we had at, by the way, you guys had a question about C equals 1 null states. I have some thoughts about that right at the end of the class, so maybe the next class. There's I think something interesting there, but let's not get into that here. Okay. We had this 1, 2, and 2, 1 curves. This was for level 2. We had this diagram. So, of course, we're going to look at various other levels, but let's first look at level 2. At level 2, it immediately follows that any point that lies inside here corresponds to non-unitary representations, because all eigenvalues were positive. Up here, this is the only curve to cross. Okay? Fine. Now, so what we've done is rule out all of these points, but we haven't yet ruled in the points that lie outside there. This is what Pinak said. Okay? There's certainly the possibility that some of these points will be ruled out by considering some higher level. Okay? Now, when we look at, let's draw the kind of curves we get at higher levels. So let's say that we go to level 3. Okay. So we go to level 3. So we go to level 3, we get a curve that looks like there's the curve that corresponds to 3, 1 looks somewhat like this. It also touches C equals 1. All of these curves touch C equals 1. We'll see that at some point. Okay. also touches c equals 1, intersects the path for 2 comma 1, okay, but covers some further region. Okay. Also, this remains a curve at level 3, because you remember that anything that was a null state at level 2 is also a null state at level 3. You remember the structure of that determinant. Now, these points, if we looked at level 3, we would have to think carefully about whether they were allowed or not. Okay, we would have to look at the power with which the level 2 state came, whether that was even odd. Okay, however, that's not relevant because it's already been ruled out from consideration of level 2. Okay, these points, on the other hand, are related to infinity by cutting just one curve. So they are ruled out, and so on. So we get a whole very large set of points ruled out. Now I want to argue that that these set of points that are ruled out cover almost everything along the lines of what Pinnock was saying. Okay, and in order to make that argument, I'm going to look at this. In order to make that argument, I'm going to look at this form of the equation. Okay, let us see what happens to these curves when we set c equals 1. Okay, so when we set c equals 1, what do we get? First, this h naught goes to 0 because c is 1. Second, this point goes to 0. Third, this number becomes 24. This was plus minus. That number becomes 24. So square root 24 and square root 24 cancel each other. So this alpha plus minus become plus minus 1. Okay, so at c equals 1 we get HRS takes this extremely simple form. It's r minus s, the whole thing squared divided by 4. Okay, note in particular that the number only depends on r minus s and not on r and s separately. So we have two different values of r and s with the same difference. They hit the c equals 1 curve at the same point. Okay, so let us suppose we take some value of r minus s is equal to p, we fix p, and we look at different values of r and s, all of which have the same difference. There's an infinite number of such points. Okay, of course, to access these different values of r and s, we would have to go to higher and higher values of the level. Okay, but these curves, when you look at that thing, you can easily convince yourself that the curves do the following thing: that the guys with low values of r and s go and hit it at this point like this, but as you increase r and s, keeping r minus s fixed, this becomes more and more like this. Starts almost hugging the c equals 1 line. Okay, so suppose you've got some point in the neighborhood. Suppose we take this, there's this curve which touches c equals 1. So all these points are ruled out at this lower value of the level. Now we go to some higher value of the level that rules out all these points. Then we go to some higher value of the level that rules out all those points. And this goes on all the way up to the c equals 1 axis, because these curves, as you take, if you do take r minus s fixed, but r and s going to infinity, okay, these curves start hugging the c equals 1 axis. Okay, so all points, this kind of argument can be used to rule out almost all points in as possible unitary representations when c is less than 1. So the allowed set of possible unitary representations when c is less than 1 is very, very limited. Okay? Now at some point in this course, maybe in the next 5 lectures, we will actually try to, or maybe when we study cosets of Weizmann-Witten theory, I'll have to see. That is actually the cleanest way of The cleanest way of understanding this unitarity is to represent minimal models as cosets of Wessel-Witten theories.
What about the points on the curves themselves?
The points on the curves themselves, well, you see, if you've got a point on this curve, that is not by itself ruled out, but it might be ruled out by considering a higher level. Okay? So this is an analysis you have to do in detail. Okay? Because you have to make sure that you can reach the point on that curve without without going twice. Okay? And exactly this kind of argument, in the end, when you go through it in detail, gives you the following result. Okay? At the moment, I'm just quoting it. As we go on with our studies, we will see more and more aspects of this. Some aspects of this we'll see in 3 or 4 lectures, and maybe the final proof only when we study Wessel-Witten theories. Okay.
Is there a limit to these curves as R and S continue to increase? Or does it if
Yeah.
R and S let's say tends to infinity, then will the curve take all the region C less than 1?
Yeah.
Or is there a limit for R minus S fixed?
For R minus S fixed, if you look at this region here, the limit is just the C equals 1 axis. Okay? But now if you also go far enough away, so if you stay at near P, the limit is just R minus, just the C equals 1 axis. Okay? But if you take R minus S, let's say R is equal to P plus alpha, where alpha is large. Okay? And now you go up to h of order alpha, or maybe square root alpha, I can't remember. Then the curve takes some non-trivial form. Then there's no limiting form. So the limiting form is for keeping values of order 1, and then, do you understand? No. Okay. You see, this curve, of course all of this is just, you see this from here, but you look at this curve and you look at C equals 1. Now, when you ask whether there is a limit, you have to ask in what region. Okay? Let me keep a fixed window. Let me keep a fixed window of some size, let's say 1. Okay? This guy is hitting at p squared by 4, and I keep a fixed window around here. In that window, this goes nearer and nearer to just the C equals 1 axis. But if you go high up here, the height being of order r, or maybe square root r, some parametrically scaling with r, then it bends. Okay? So in some region it becomes the C equals 1 axis, but eventually it deviates from that. Clear? Okay.
But at higher levels then, another curve can come and bind more such area, right?
Yes, but the problem with higher levels is that there are other curves. So the only thing that you rule out is where you've started from infinity and you pass one curve and hit the point. If you've got to get to that point, you have to cut 2 curves. Then you've not ruled that point out. Right? Because every time you hit a curve, at least one eigenvalue is switching from positive to negative. Okay? So it could be that you've switched from positive to negative and back to positive. Do you understand? So the only thing that you immediately rule out are those points that can reach infinity by cutting exactly one curve. Now, all the curves that exist at lower levels also exist at higher levels. Okay? So for instance, when you go onto a point on one of the other curves, let me say this here. Actually, what I'm saying now is a bit inaccurate because you have to keep track of whether this lower curve appears with even or odd power. I'm assuming I'm looking at the case where the lower curve appears with an odd power. Okay, so that it changes sign. Okay, so but in that case, suppose you've got something like this. You've got this curve here and some lower curve here. Okay? So what you're not ruling out is that points on this second curve are okay. Because when you go on this second curve, you get a new 0, and that 0 may be of that offending negative norm state. Are you understanding? Okay? So basically, you're right. This kind of argument can be used to establish that the only possible values of unitary representations lie on one of these curves. Is this clear? Okay? Because you see, when you've gone from here to here, there is a possibility that it's unitary, because here you had a negative norm state, but here something went to 0. So some state went 0 norm. Could be that the state that went 0 norm was the bad state, the one that was negative norm. Okay? But of course it calls for a massive conspiracy for this to happen. Typically it will be some other guy that goes 0 norm. That goes 0 norm and then will go negative, right? So this massive conspiracy has to happen. And only that will allow you to have a unitary theory.
Also, there should be odd number of distinct intersections by the other curves, right? Because if two intersections do collide at one point, then that can be counted as a signal one. So that odd number can come into either one. So that might be a bit further.
Right. At this point, there is absolutely no argument, I mean, from what I've given so far, that this is not allowed. Right? Because here this was number 1, because it was the first guy that is got negative here. And then you've reached here, maybe the second guy. That could be odd, we don't have to think too much, but it's got some 0 norm states. If one of those 0 norm states was the offending guy, that might be okay. Is this clear? Okay? The end result, you might have thought from this analysis. Okay? You might have thought from this analysis, it's just like it's totally weird that this could happen. You might have thought that, okay, it's some fiddly stuff, and in the end, when the mathematicians get their act together, they will prove that there are no unitary theories with C less than 1. Except you are not allowed to think that, because we've already studied one unitary theory with C less than 1, namely free fermions. So clearly the theory with C equals half exists. We studied it in great detail. We've looked at, modular invariant partition functions, a great theory. Okay? So it can't be that this analysis is too restrictive. It can't kill everything. Okay? But going through this kind of thing in great detail, I'm just right now telling you the answer. Okay. The answer is that this theory, unitary theories first only occur at discrete values of C, not at every value of C. These values of C are 1 minus 6 to m plus 1. It's the same formula we had here. Except now, there m was a real or complex number. Here, m is equal to 2, 3. Okay? M is forced, from this way of writing it, m is forced to be an integer. Notice that in the limit m goes to infinity, C goes to 1. So we've got to notice also that that when m is equal to 2,
When n is 3, then
when m is equal to 3, we get 3 into 4. Yeah, exactly. When m is equal to 3, we get 3 into 4. So this is half. This is the null state for the Ising model. When m is equal to 2, on the other hand, we get C equals 0. This is simply the trivial theorem. Okay, so m is formally allowed to be 2, 3 up to infinity, but for interesting theories, m has to be 3 and larger. Okay. That is point number 1. Okay. Now, when we are at this value of C, what values of H are allowed? Okay. Answer to that is that the allowed values of H are HRS of M is equal to, it's the same thing, but I'm just writing it again, M plus 1 R minus MS, the whole thing is square minus 1 divided by 4m into m plus 1, except that we have the following restriction and ranges. S 1 is less than equal to S is less than R. So S is smaller than, so S and R of course are integers. They have started at 1, that remains, but S is less than R, and R of course was always greater than equal to 1, is less than M, less than M. Okay. So the only unitary modules, okay, the only unitary modules exist at these values of M and therefore these values of C, and at those values of C there's only a finite number of allowed weights. There's only a finite number of allowed weights, okay, for unitary representations given by this formula. Okay, just to make this a little less abstract, let's work this out in this simple special case M equals 3. Louder? Null states, yes?
Can they act as highest weight representations of some modules?
Yes. In fact, null states are always highest weight representations. Yes, they are, they can, and they will. Okay. Let me finish saying this and then I will try to explain why that is always the case. Okay. Fine. Okay. So let's take the case M is equal to 3. Okay. So when we have the case M is equal to 3, what are the possible values of R and S? First, let's look at this guy. R is limited to range from 1 or 2. So we can have R is equal to 1, R is equal to 2. Those are the allowed values. Now what about S? If R is equal to 1, there is no such S. Okay. But when R is equal to 2, okay, we can have S is equal to 1. Okay. So we've got these values. R is equal to 2, S is equal to 1. Now let's plug that in. Okay. So we have M is equal to 3. So we get 4. R was 2, so into 2 minus 3 divided by 4 into 3 into 4. Square minus 1. Okay. And this is equal to, so that's 8 minus 3, 5. 5 square minus 1, so 25 minus 1, so 24. Divided by 4 into 3 into 4. Have I done this right? And then we get half. Okay. Okay. Oh. And why are we not seeing the other representations? What about the 1 by 16? Sorry. Yeah, there's another primary. Why am I not seeing it? That's a 1 by 8 or 1 by 16, right? 1 by 16. Yeah, give me 1 minute. Am I saying it wrong? That's what I'm reading here. I've written it right now. Maybe there's one of them is an equal to. Just what if S was allowed to be equal?
S is the limit of S is between 1 and m minus 1, and the limit of the limit of R is between 1 and m minus 1 equal to both sides.
Yeah, that's correct.
The other is equal to.
Equal to.
Yes.
Okay, thank you. Okay, thank you. Let's do this. Let's do this again. Thank you. So let's see.
So R equal to 1, S equal to 1 is 0.
R equals 1, S equals 1 is 0, which you'd expect for the trivial. You know.
One more here.
Yeah. So yeah, that's S equal to 2. Thank you. This makes more sense. Thank you. Okay, so let's do R equals. So R equals 1, S equals 1. We get 0. That's the identity. And then there is R is equal to 2, S is equal to 2. So let's look at that. So that's 3 into 3 minus 2. No, 4 minus 2. 4 minus 3 into 2. The whole thing square minus 1 divided by the same 4 into 3 into 4. Okay. So that's 3 by 48. Yeah, so that's 1 by 16. Thank you. Yes.
You expect identity.
Yes, you expect identity. Yes. Absolutely. So it will always be that S
Equal to R equal to 1 will be.
S is equal to R is equal to 1 is identity. That will always be an allowed value. Yes. Okay. And this is exactly the dimensions of the operators in the Ising model or in the free fermion. Right? We found this 1 by 16 as the ground state of the Ramon sector, if you remember. Okay, so the ground state of the Ramon sector, the ground state of the non-trivial identity operator in the NS sector, the psi, and identity were the 3 operators. Okay.
So before going to m equals 3, why don't we were checking at m equals 2, because at that point HRS will be discrete, right? And it should not be discrete, it should be continuous.
Why?
You have e to the power I kx at c equal
M equals 2 is not C equals 1, it's C equals 0. Yeah. So the fact that the number of primaries, sort of goes to infinity as we take m goes to infinity is along the lines of what you're saying. Right? We get more and more primaries as we go nearer to C equals 1. Right? But that was the m equals 2 was just a trivial theory. C equals 0, just one state. Yeah. And now that you guys have corrected my my regions, we see also that the trivial theory does have one primary. It has R is equal to S is equal to 1, which is the identity primary.
So we can't say anything about C equal to 1.
Yeah, we can't say anything about C equals 1 through, yeah. It's a bit of a singular limit. However, the fact that these curves hit the C equals 1 thing, I think has explanations in terms of null states of current algebra. Maybe at the end of this class I will discuss this. I haven't worked it out all in detail. Maybe next class. Okay. Okay, excellent. Please go on.
also from the expression of this HRS,
Yes.
If you switch R and S, are you ruling out the lower curve and just taking the upper curve?
Right.
Because S is
You see, we're ruling out most of the curve. What we're doing is one point on the curve
yes.
that is allowed.
No, but there were two curves, right? H21 and H12.
Yes,
And you were saying that H12 will not be there.
that's correct. Okay, but we're saying more than that, right? Because we're not all points on the curve. There's exactly one point on that curve. Because it's a given value of C. So it's correct that it's one point on the curve, not 2 points on the curve.
Yes.
That's correct. That's correct. There is this thing that these guys like to call first intersections. The points where these things exist are on intersections of two of these curves. Okay? And these intersections have to satisfy some properties. Okay? And these intersections will either happen on the lower curve or on the upper curve. Not on both. That's the
Just on the upper curve, right?
yeah.
And why is there a restriction?
Because it has to be unitary. You see, the way these guys. No, typically two curves. Yeah, even the fact that they lie on the intersection of any curves you would have to is surprising, right? I mean, from this algebraic thing. No, but I mean, certainly if you look at the lower ones, it's obvious that they lie only on two curves. I am not sure if there's probably a proof. Let me just, there's probably. Let me, in this case, let's look at level 3. And look at this diagram. There's this guy, and there's this guy. I'm not drawing it well because both hit C equals 1. So there's this guy, and there's this guy. Okay. This is one of these points that are first intersections. This is this intersection of this curve. This is like the 3, 1 curve. Where the 1, 3 or 3, 1 I'm not distinguishing. Okay. This whole thing. Okay, and this is the 2, 1 curve. Whether 2, 1 or 1, 2, I'm not distinguishing. The point is that the unitary theories lie at the intersection of these 2 points. Okay, now this intersection does happen to lie on the upper part of the 2, 1 curve. That's why it's not on the lower part.
Shouldn't the origin be counted also? Because it's like this one.
Yeah, the origin is counted because it's a identity operator. Yeah, this is also in some sense a first intersection. Okay, these points can be approached at a level 3 like this. Okay, so in the approach you can get to this point. Okay, so level 3 analysis is not ruling it out because there's a null state, but that's fine, you can mod out by that. The difficult thing is to show that higher level analyses don't rule it out. Okay, you could ask why this point rather than, let's say, this point? This is not unitary. Some higher level analysis will show you that that's not unitary. The difference between these two is that this is the point of these intersections.
And this formula that we had proved just earlier, that was obtained using by analyzing all the levels.
It's, you see, by that you rule out most things is by analyzing all these curves. Okay, ruling in is a little more difficult. Okay, because you have to keep track of this kind of thing. When something was negative norm, and then something becomes null, is it precisely that guy that becomes null? Okay, perhaps the cleanest way to rule in these theories is to explicitly construct them. Okay, which we will at some point in our course do. Yeah. But you see already that anything meet these conditions is a bit of a miracle. It's already clear that anything that does meet this restriction will lie on one of these curves. Yeah, these are the only kinds of things that we will not be able to rule out. Okay, these guys lie on these curves, but they're discrete points on these curves. Okay, and where they lie, it's at this intersection of the points. We will understand the structure more and more as we go along. Okay, good. Any other questions or comments? Okay, fine. So let me immediately start trying to use some of the structure. Okay, let's immediately start trying to use some of this structure.
Similar parameterization of these allowed theories in the other formula? Because there C equal to 1 doesn't seem like a singularity. Here you wrote it in terms of this M, right? Being but there M going to infinity is C equal to 1. But
Yes.
The third
You're asking what happens to T?
T.
Okay, I can write down the formula for
C equal to 1, T is just 1, right?
for C equals 1, T is 1, correct. T is 1. Good, T is 1, correct. You want to know at what values of T this happens? These values?
I mean, what are the values of H is there?
Same, sorry. In the limit that C goes to 1? Okay.
Here it was a bit singular.
When
It was infinite.
okay, but we can still, we will still get, let's take M large, but not infinite. Okay, and then we will take the limit to infinity. So let's work that out. So suppose we have, our R was less than M, so less than equal to, like Karthik said, M plus 1, and S was less than equal to R. Right? Let's put that in when M becomes large. Okay. So when M is large, we can forget about difference between M and M plus 1.
It's just R minus S whole square by 4.
Exactly. It's R minus S, the whole thing squared by 4, at least.
The leading.
Yeah. At leading order. Now, this R minus 1, the whole thing squared by 4. But all of these are what? These, what's happening here is that there is this curve. There is this, you remember where the curve hit the C equals 1 axis. Okay. We have lots of operators here, but for every value of R minus S. Okay. And yeah. Now, yeah. So your question is can you see this somehow going to the C equals 1 theory? Perhaps it will I don't know. Perhaps it somehow goes to like a compact boson, which had discrete values of but yeah, this does look a little bit like k squared by 4, right? So maybe it goes to actually this is related to the other comment I wanted to make, that these null states are coming from look like they're coming from current algebra, which is exactly what you get in the case of a compact boson. Right? Yeah. So perhaps there is a sense, okay, I don't know, but perhaps there is a sense in which these theories tend to a particular C equals 1 theory. This, as you say, you're certainly not getting the continuum. Yeah. 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 When we, right, you see, as we will see when we continue our studies, okay, let me make a little side remark since this question is coming up about the relationship between these theories and the free boson. Okay, this little side remark. The side remark goes like this. Suppose we didn't know about this fancy conformal field theory, but we were just trying to construct conformal field theories in 2 dimensions using what we know about quantum field theory. Okay? Well, there was this very successful construction of phi to the 4 theory in 3 dimensions, basically using the epsilon expansion starting in 4 dimensions. Okay? So you could ask, can we make more such constructions of interacting theories? Let's try that. Suppose I want a theory that's stable, so I'll always take phi to the power 2n. I want an interaction like phi to the power 2n. I want to construct it in an epsilon expansion. Okay? So I want to construct this theory. So I want to construct it in an epsilon expansion around some dimension. Which dimension is correct for starting with this theory? So the dimension that's correct is the dimension in which this operator is marginal. Now in dimension d, the dimension of phi is equal to d minus 2 by 2. Okay? So the dimension of this guy is n into d minus 2. It's 2n into that, into d minus 2 by 2. We want this to be equal to d, because this has to be marginal. Okay? And therefore, we find, now we solve for d. So nd minus 2n is equal to d, or d into n minus 2, n minus 1, thank you, is equal to 2n. So d is equal to 2n divided by n minus 1. Notice that this is equal to, which is equal to 2 plus 2 by n minus 1, where I've written n is equal to n minus 1 plus 1 and cancelled. Okay? So it's 2 plus something small as n goes to infinity. So you see that there are these theories which are marginal in 2 plus epsilon, in 2 plus some number of dimensions, and the number of dimensions goes to 0 as n goes to infinity. So suppose we try to construct the theory in this fractional dimension, then work in an epsilon expansion and choose epsilon so as to make the dimension 2. When n is 3 or 4, there's some luck that we can take epsilon all the way to 2. I mean epsilon so that the dimension becomes 2, because we're finitely away. But when n is equal to 1,000,000, there's almost no luck involved, because we have to move just very little distance, so the answer will be perturbative. Okay? So this whole set of theories, okay, this whole set of theories that you can construct, okay, definitely exist in 2 dimensions. They definitely exist because we can construct them perturbatively. Okay, at least for n larger than some critical value. In fact, it will work for all values of n. Okay, but it's clear that it should work for n larger than critical value. Okay, this is the sense. We will identify as we go along with our studies, we will identify these constructions in the space of minimal models. And this is the sense in which these guys become like free bosons. How, you see, it's never quite that it becomes free, because there's always a potential. Okay? It's never quite that it becomes free, there's always a potential. And this potential is not negligible, because it's phi to the power n, and that's a pretty steep potential. But it's negligible, it's more and more negligible around 0. It's flatter and flatter around 0. Okay? So for a while, you just don't see the potential. But then you do, because you're in a box. Okay? So really this construction, as you take n goes to infinity, you should expect it to give you free bosons in a box.
Right.
Okay? And that, I think, is what we're seeing in this discrete dimension. This box. Okay? So the sense in which we get the free boson, you have to be a bit careful about. Locally it becomes a free boson, but not in the sense of boundary conditions. This is why I was saying it's sort of like being on a circle, because a box and a circle are not very different. Okay? Yeah. This is the reason we're not getting the continuum, because certainly the continuum sees the potential. Right? Okay, it's clear? Okay, excellent. But again, all of this we will study. We will see exactly the relationship between these theories and the minimal models and so on.
Yeah, so I have a tangent.
Yes.
So if you look at every process of isomorphism theories, if you go to these large n limits, can you construct C is equal to 1 sort of theory?
You want like, so certainly you can construct the minimal models.
But so I remember some formulas where it depended on n. When you go to n going to infinity sort of limits, you go to c.
You know, I think the thing you're thinking of is something like this, that if you, a Westerby-Witten model is in the end a sigma model on a on a curved space. The curvature is being set by the level.
Yes.
In the limit the level goes to infinity, the curvature goes almost to 0.
Right.
So, so there are no, so it's like your circle, if there is a, then you take a coset, so it becomes not, I don't know, not 2-dimensional or not 3-dimensional, but yeah, 1-dimensional. If you take that very large, it's maybe, I'm not, yeah, that sounds reasonable actually. It sounds reasonable. You take the right kind of coset, it sounds reasonable. In the k goes to infinity. Right? Yeah, it sounds reasonable in that limit. Okay, excellent. I'm sorry we're going so slow. Let's keep going. Now, the fact that these theories, these representations that appear, that exist, the fact that they lie on this curve, okay, tells us that where these representations exist, they have a null state. Right? Because this state, this was the place where the determinant vanished. So the Koch determinant vanished for that level and every level high. Okay, so you have a null state. Okay, and the fact, as I said at the beginning of this class, the fact that we have a null state is the key to the solvability of this theory, of these theories. And I want to explain this point as in a little more detail. Okay, so let us first work with this, okay, so we want to work with a particular null state. Okay, well, let's look at the theory with m is equal to 3. In that case, r had to be 2 or lower, s had to be 2 or lower, and we had two options for, I mean, apart from 1, 1, which has null states but it's too trivial, we have two options. We have r is equal to 1, s is equal to 1, or r is equal to 1 and s is equal, r is equal to 1 is equal to 2. So let's consider the case r is equal to 2 and s is equal to 1. When is the first level at which we will see this null state? Well, our condition was that rs had to be less than or equal to the level. Okay, so we see this null state first at level 2. Okay, so this is the null state corresponding to the operator psi, right? The dimension half operator. Okay, so we should be able to see that at level 2 we have a null state. Okay, now how is the state going to turn out to be null? So we've got, let's say that we're at this value of c, the value of c which is c equals half, the value at which we have m equals 3. So we're at m equals 3, c equals half. Okay, we expect we will have a null state corresponding to r equals 2, s is equal to 1 at level 2. Now, what is the most general state at level 2? Exactly. So that's L minus 1, the whole thing squared, into alpha plus L minus 2 into beta. This is acting on our primary state. Let's call that psi. This is the primary state of dimension half. Okay? Now we know a lot about this system. We know we expect that this state is going to have dimension half. We expect C is going to be half, and so on. I'll pretend we didn't know this in the analysis that we are doing and get some of it out. Okay? So let me follow the notation here. Let us okay. So we want this chi here. So let's call this, I will taking a factor of beta overall just up to normalization, and I'll follow this guy's notation, he calls it eta. Okay. So this is our state, and this is the state we're going to call chi. Okay. Now let's think of, there is this question that Pinnock asked sometime in the class that we're going to review. Okay? Suppose we have a null state. Okay? Suppose we have a state chi. Okay? That has the property that it is both a descendant. Okay? So it's of this form. It's a descendant of psi, but is also by itself a primary, which means that suppose we can find chi for which Ln of chi on chi is equal to 0 for all n greater than 0. This was our definition of primaries, as you remember. Okay? So suppose we have a state that is both a descendant and a primary. Okay, now I want to argue that every such state will automatically be null. This is obvious. Why is it obvious? Because consider chi, let's do it the other way. Consider chi, inner product of chi with any state that is of the form a L minus 1 the whole thing squared plus b L minus 2 on psi. Right? You see chi is a descendant of psi. I want to consider its inner product with all other descendants of psi. Now the inner product must necessarily vanish if this descendant does not have the same level, because inner product of states with different energies is 0. So I only need to consider the inner product with arbitrary states at level 2. This A and B has nothing to do with that eta. Okay? But this is the same as A star into L1 the whole thing squared on, define the vector z theta is equal to A star into L1 squared plus B star into L2 on chi. Then this is the same as theta psi. Right? Just by taking these into that. But we have claimed here that this chi state, whatever it is annihilated by all positive L's. So this is 0. Okay? So if you have a state that is both a primary and a descendant, then it is necessarily orthogonal to every state, every other descendant of the original primary, including itself. So in particular, it's a null state. Okay? So this is the basic structure of null states. Null states are states, okay, that are primary, that are descendants, but they're also primaries. Okay? And because of that fact, they are orthogonal to every other state in the in the module, including themselves. Because they are orthogonal to every other state in the module, they can be consistently removed from the theory. Because in the matrix of inner products, any inner product you make, in quantum mechanics you do some process, right? The amplitude to go to this state is you start with some state, act with some operators, and then you take an inner product. But because this state is orthogonal to everything, that amplitude always vanishes. So you can just remove that state from the theory. This is the same argument that we use in BRST quantization. In removing states that are BRST exact, because they are orthogonal to every other state in the theory. Okay? So these states are like pure gauge states and can be removed from the theory because they are orthogonal to every state in the theory. And you see the structure of these things, because they're primaries, you remove not just them, but of course all their descendants as well. Because the inner product of any descendant of the state is related to the inner product with this primary by the usual technique, right? By the way we computed this inner product matrix. Okay? So the structure of this theory is this. You have these null states that are primaries as well as descendants. Okay? These primaries are null, they are orthogonal to everything else in the game, and we're going to remove them. We're going to declare that they are the zero state. Okay, that's how we're going to try to solve the theory. That's how we'll get a positive definite inner product in unitary theory, despite having null states. Because these null states are going to be declared pure gauge. Is this clear? Okay, so now let us try to understand this at level 2. Yes, you can get descent. Sure. Because you can take the state and act with L minus 1 on it, L minus 20 on it.
What about those two?
All of them are orthogonal to everything. You see, because the inner products of descendants can be, by the same algebra that we make the inner product matrix, can be related to the inner product of primaries. Okay? So, since the primary itself is orthogonal to everything, the descendants are also orthogonal.
Yeah, that is why you can take a factorization, right? You factorize module by module.
Exactly. 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 So, now let us continue. Let us try to make a state at level 2 that is both a descendant and a primary. Okay? So, let us try to make a state that is of the form a into L minus 1 the whole thing squared plus, let's stick to that form, eta into L minus 1 the whole thing squared plus L minus 2 acting on psi. The condition that it's a primary is the condition that it's annihilated by L1 and L2. In fact, if something is annihilated by L1 and L2, it's annihilated by every positive L, because you can make L3 by commuting L1 with L2 and so on. Okay. So, the condition we want to impose on this state is that L1 on this is equal to 0 and L2 on this is equal to 0. Okay, so let's do this algebra before ending this class. Okay, so we want L1 on this is equal to 0 and L2 of this is equal to 0. Let's start with L2, that's the easier calculation. So we have L2 into eta L minus 1 the whole thing squared plus L minus 2 acting on psi is equal to 0. Okay, now basically we always do the same thing. We take this through to the end, L2 kills psi, and then whatever's left is left. Okay, so let's do that. Let's first do L2 with L minus 2. So what was our algebra? It was Ln was equal to, somebody please remind me. C into what? M square minus 1? M into M square minus 1. Okay, thank you. So let's do it with L2 with L minus 2. L2 with L minus 2. We get 4 L0. 4 L0 plus, this is delta. What? Sorry? 12. Plus C by 12 into 2 into 3. So C 2 into 3 by 2, good. By 2. Okay, that's what we get with taking this guy through here on psi. Okay, now what do we get when we take this guy through? Okay, so we have L2, L minus 1, L minus 1. Let's first take L through to L minus 1. Okay, so this is equal to commutator. So this is 3L1 L minus 1 plus L minus 1 L2 L minus 1. Now this L2 L minus 1, whatever you get will have positive number, so it will annihilate the state. Okay, so this guy is going to annihilate, so we can forget about it. Okay, what remains is this guy. So we have still to take this guy through this guy, but when we take this guy through this guy, we just pick up 2L0 plus 0 because M was 1. Okay, so we get 3 into 6L0 L0 on psi. Okay, so if I've done it right, what we got by acting on this thing was 10 L0. Thank you. Thank you. It was 4 plus 6 eta. Eta L0 plus C by 2 on psi is equal to 0. Now let's say that the value of the weight of psi, which in the end will turn out to, for the problem of interest, will turn out to be half, but let's say that it's h. So we've got one equation. The equation is that 4 plus 6 eta into h plus c by 2 is equal to 0. Okay, this is the first equation for it being a primary state. Okay, now we have the second equation, so let me continue here. The second equation comes from acting with L1. So we have L1 on eta L minus 1, the whole thing squared, plus L minus 2 on psi is equal to 0. Okay. So let's do this. Let's first again do L1 with L minus 2. So we get, it help me, so we get 3 L minus 1 on psi. Okay. Now what about this guy? This guy is eta. Now first L1 with L minus 1 gives 2L0 L minus 1. Okay. Plus L minus 1 L1 L minus 1. Now L1 L minus 1 is 2L0. Because L1 will hit. So this is 2L0. So 2 eta L0. Now L0 acting on state is H. L0 acting on L minus 1 of state is H plus 1 because L minus 1 raises H by. Okay. And so we get 2 into 2 h plus 2. Sorry, 2h plus 1. Eta into 2h plus 1 into L minus 1 of psi, that has to vanish. Now we are assuming that our state has a null state at level 2, but no null state at level 1. Okay? Actually, the only module that has a null state at level 1 is the identity module. We proved that, if you remember. Because L minus 1 on something equals 0 means derivative of that thing is equal to 0. So L minus 1 on psi is not 0. Therefore, this must be 0. Okay. What about the sign? Yeah, sorry, what happened to the?
3L minus 1.
And I've missed some eta as well, sorry. So I'm so sorry. There was, let me do it again. This is, yeah, this is true. Yeah, so it's a 3 plus this. So we get 3 plus 2, this, which one came with the eta? Second one. 2 eta into 2h plus 1 is equal to 0. Okay. So you see, what is the structure of our equations? Okay. The structure of our equations is that we got 2 equations for this variable eta. So at generic values of eta, we will not be able to solve, generic values of h, we will not be able to solve this equation. There has to be one condition between h and c for this condition to, this problem to admit a solution. And that condition, of course, will be the condition that we are on that h21 curve. Right, because if we had a null state at level 2, then the determinant at level 2 had to be 0. But that condition was being on this h21 curve. Okay? So what this exercise has given us 2 things. It will allow us to recover this relationship between h and c that we will see, but it's done something else. It's allowed us to find the exact value of the null state, because we can use this relationship to solve for eta. So we have eta is equal to minus 3 divided by 2 into 2h plus 1. Okay? Now we plug, so this is eta. We found eta. But this other equation also has to be satisfied. Okay? So we plug that back in here. This gives us a constraint now relating just h and c. And that one can check is just the old constraint that we got. Okay? So the null state at level 2, we've done this little exercise that has allowed us to do more than just claim there exists a null state at level 2. We have found it. Okay? And I suppose in the next class what we will do is, okay, let me just tell you what we're going to do. I'm so sorry we're going so slow. Yeah, maybe I'll speed up from next class. Anyway, so what we're going to do now is to use this null state to deduce consequences for correlation functions of a theory that has this null state. You see, all that we are using at this point is that we're lying somewhere on that h21 curve. Okay? When we put in that we're lying at this particular point, we'll learn even more. But fix the value of h or c, or yeah. Okay? Just that we're lying somewhere on this. We've not put all that, that stuff that comes from higher level analysis into this. We're just somewhere on this curve. But already we will be able to learn many things. Let me just give you a teaser for what we will be able to learn. Yeah, what we will be able to learn is this. We'll take this equation. Maybe I can quickly say it. I mean, in equations. Suppose we have we're going to try various exercises. You remember that we got a differential equation that the action of L minus 2 or L minus 1 on some operator, okay, the action of L minus 2 or L minus 1 of some operator was related to some sort of differential operator acting on the remaining operators. Now we're going to put in the condition that this guy annihilates our operator. Okay, so let's look first at 2-point functions. Let's take a 2-point function of this operator with something else. We already know because last time we deduced the form of allowed 2-point functions. You remember it was 1 over z minus z1 minus z2 to the power 2h, and it had to be 2-point functions were only non-zero when two operators had the same h. Okay? First question, this differential equation should be automatically obeyed for 2-point functions. Otherwise, it will be the statement that such an operator cannot exist. Okay? So what we will do, I think we'll do it next class, what we will do is look at this differential operator, act it on 2-point functions, and see that it's automatically obeyed, as long as h1 was h2. We will find that. Nothing comes out of it. Already at the level of 3-point functions, though, something interesting happens. Okay. Now, we also know the form of 3-point functions. Suppose we have an operator with this h and two other operators of dimensions h1 and h2. We don't yet know what h1 and h2 are. Okay? If we already know the form of the 3-point function, 1 over z12 to the power h1 plus h2 minus h3 by 2 and so on. Okay? Now, once again we've got a differential equation. We act that on this 3-point function. Either it's automatically identically obeyed or it's not. Turns out it's not identically obeyed. Okay? You get some number made out of h1h and h2 and h times an expression. And that number has to vanish. You can get many expressions, but it's always the same number. Okay? And so you get one constraint, and that constraint is a constraint on h1, h2, and h. So it tells you that if we have a 3-point function between this operator and two other operators, h1 and with dimensions h1 and h2, for generic values of h1 and h2, that 3-point function has to vanish. The 3-point function can only be non-vanishing when h1 and h2 themselves take particular forms. Okay? And then we will analyze what happens with 4-point functions. Okay, and we will get much more information. We will get enough information, more or less, to determine the correlation functions. Okay? Oh, okay, so all this we will try to do next.